All right, hello once again. This is Jeff Scott. I've been coming at you with JavaScript, courtesy of Murox JavaScript 2nd edition. We're on Chapter 14 of 17, how to work with closures, callback, and recursion. All right, first thing we'll cover in here are closures, including how they work and how they're used. Closures protect your code, and they can help with specific looping problems. From there, we'll go on to callbacks, talk about how they work in some examples. And finally, we'll go on to recursion. All right, and with all those, we'll take a look at some apps and some other stuff, so you'll be able to see them. These, again, are very advanced topics. I wouldn't think that you could just take, a listen to this tape and think, well, geez, I know how this works now, because there's a lot to them. So our objectives: apply closures, IIFEs, which we'll get to in just a bit, callbacks and recursion in applications, describe how the scope chain works in JavaScript, describe the use of closures, including how to use closures to create private state, describe the use of immediately invoked function expressions, which are those IIFEs, including how to use them to create block scope, describe the use of callback functions. In general, explain how recursive functions work. All right, what this example is supposed to start showing you is what's referred to in JavaScript and in other languages as the scope chain. And what the scope chain means is what can be seen, all right, what can be seen and used by other objects. It starts with a global scope and it works its way down. All right, so if you notice up at the very top, we've got var g equals I am global. Okay, so the idea with this is it's a global variable. All right, so it's known throughout this entire program, and it can be used anywhere, and it can be technically changed anywhere in this entire program. Then we've got a function a global function named outer function. All right, then within the outer function, it creates a local variable named O and a local function that's named inner function. Finally, within the inner function, there's a local variable named I. And at various points in here, they come in and they put log statements in here. All right. So what they mention is when you're talking about global scope, in other words, what's available to everyone, everything throughout the program, basically, it's G. The G variable. In other words, the code can't exactly do what's called move down the scope chain and see other variables in either of the functions. When you're in local scope, meaning when you're either inside of the outer function or when you're inside of the inner function, the variables G and O are going to be visible. So the code can see its own scope, and it can move up the scope chain to see global scope. All right, when you're in the inner function, all three variables are available. So in other words, the variable I is available, the variable O is available, and the variable G is available. So they mention in here, objects that are created within other objects have access to their own scope and the scope of the object that contains them. So in English, this has access to everything in here and everything in here. So object visibility moves up the scope chain, not down. An object in the scope chain will be available as long as something refers to it. This is true even when the object has finished and is out of scope. Well, that's very, very little beginning. And again, you're going to have to read this, and you're going to probably have to read it again and again and again before it makes a lot of sense. All right. So starting on page 432 in the text, the author begins a discussion of what closures are. And as you can see, and this is shown on 433 also, a closure is an inner function that has access to an outer function's variables. So in many ways, it's kind of like this. It's an inner function which has access to the outer function's variables. Closures are created when a reference is made to a variable, object, or function defined within another function. One common way to create a closure is for an outer function to return the inner function. Closures keep extra scope in memory, and these can cause performance problems when they're overused. So, with the example in here, we've got a function that's called create click counter, and it contains a variable named count that is set to 0, and it has an inner function named click counter that increments the variable by 1. The count variable is in the outer function. It's not defined in the inner function, but it's used in the inner function. What this means is that the click counter function is technically returned by the outer function, and that count will stay alive, even though the outer function is finished. Next, we've got an event handler function for the Windows onload event, and that attaches event handlers for two different buttons. As you can see there, first button and second button. So technically what this means is the count variable is available in the scope chain of the button it's attached to and not anywhere else. When you work with closures, it's important that you remember that they work by keeping extra scope in memory. So in other words, they're taking up extra memory, so you should be judicious in how you use them. All right, but let's talk about how they can be used. So they go back and they recreate the rollover application from Chapter 13. In fact, the rollover application in Chapter 13 included closures. So the code for this is shown right here. So the create rollover function contains two inner functions, one called mouseover and one called mouseout. Each of the inner functions refers to the local variable of the outer function. Since the inner functions are attached as event handlers, any references to them stay alive, which means the references to the local variables of the outer function also stay alive even after the outer function has been finished and has gone out of scope. So each call to the create rollover function creates a closure that has its own variables. This is how each rollover stores the image information that's sent to the outer function. So all that's fine and dandy. So you've seen a little bit, but how do you use this stuff? Well, again, the properties and methods of the slideshow object back from Chapter 13. All of these properties and methods of a JavaScript object are publicly available, meaning that an object's critical properties and methods, it's possible for you to overwrite those. If you want to protect an object's properties and methods, you can use closures to create what's called private state, and we'll talk about that in just a minute. First, let's mention what each one of these is. Timer is a property that holds a reference to a timer object. Nodes is a property that contains an object that holds references to image and span tags. IMG is a property that contains an object that holds an array of image objects. Play is a Boolean that indicates whether or not a slideshow is playing. Speed is a number property that indicates in milliseconds how often the slide should change. Stop slideshow is a method that stops the timer. Display next image is a method that gets and displays the next image. Set play text is a method that toggles the text of a pause resume link. Load images is a method that accepts an array of slide objects, preloads the images, and stores image objects in the img.cache array. Start slideshow is a method that accepts and stores references to image and span tags, starts the timer, and stores a reference to the timer object. And toggle play, which is a method used to start and stop the slideshow. Now, in the previous chapter, we saw an app that worked with images and timers to create a slideshow. All right, the slideshow library consisted of an object literal that was named slideshow that had all the properties and methods inside of it, the ones that we just went over. The table that you see in front of you right now shows how many of the properties and methods are needed by code outside of the slideshow object. In fact, no properties and only 3 methods are called by outside code. Now, we have in here with load images, remember, that's the onload event handler. That's where we want to set that. Start slideshow, we also want to set in the onload event handler. And toggle play has to be set in that hyperlink that either is going to say play or pause. Now, with many programming languages, you can code public and private keywords to designate which properties and methods should be available. Java is an example of this, but JavaScript does not, at least currently, offer those keywords. They may be added in the future, but no one really knows. So until that point, you can use closures to create what's called private state for your object. To illustrate that, what you see here in this figure is how to rewrite the object literal for the slideshow of Chapter 13 with 3 public methods and the rest of the object's properties and methods in what are called private state. As I said to you before, this is really heavy stuff, okay? So normally you first define a function and then you invoke it, all right? Similarly to what you see on the screen right now. However, you can define and invoke a function in one step by adding parentheses at the end, as in this example right here. When you do this, it's called an IIFE, or an immediately invoked function expression. Since it's immediately invoked, it doesn't need to be stored in a variable. In other words, it's an anonymous function. So again, an IIFE is a function that's defined and invoked all at once. An IIFE should always be coded within parameters so the JavaScript engine and programmers will interpret it as an IIFE. Like a regular function call, an IIFE ends with opening and closing parens, which can accept arguments. Unlike some languages, JavaScript does not have block scope to protect variables in an if statement or for loop, but you can use IIFE to simulate block scope. As long as no reference to IIFE remains when it's done running, the scope is destroyed, even though the function that contains it might still be in scope. So again, block scope refers to variables that are declared inside of a block of code, like an if statement or a loop. Typically, when you do that and you declare something inside of here, you can then not use it outside of here. So if I wanted to use I outside like this, all right, I'd have to define it out here. I can't define it in here because the scope in most programming languages says that since I've defined I inside of the for loop, its scope, or where it's accessible, is only in the for loop. That's not the case in JavaScript. But you can run into problems when you do that. All right. As it says, a closure has access to the values in its scope chain of reference. That means if an outer variable changes, it will change for the closure too. So you can sometimes run into problems with loops when you use this. If you're working with closures in a loop, you can have a problem if you don't understand, as it says, those 2 points that we just went over. Those being, again, that first, the closure has access to the values in its scope chain by reference. What this means is if the value of an outer variable changes, then its value will change in the inner function as well. Second, the values of the variables in a function are determined when the function is invoked, not when it's defined. What this can mean, all right, is you can end up unknowingly incrementing a value of a loop more than once when you don't mean to do it, because it's being done, since it's inside of another function, it's being done for you. So in the system's zeal to try to help you, it's actually hurting you. So they talk about how to fix this on 442 and 443. And the author says, although a closure has access to the variables higher up the scope chain, each function has its own this keyword, which can cause problems with working with closures. If a closure needs access to the outer function's this keyword, the outer function can pass it to the closure using the bind method. Again, this is about as complex in this language as it gets. So the author next comes in here and wants to redo the slideshow application that was done in an earlier chapter so that it uses closures. In the example, it protects the variables and functions that the app needs for internal operations. If we follow this and we look here, the only difference from the Chapter 13 app, that this HTML uses a tag of type button rather than an A tag. All right, so the slideshow app works the same as it did in the last chapter. It uses a button instead of a link for the pause resume, which means that you don't need to cancel a default action, as we did back in Chapter 13 or wherever it was. The main difference here is that the slideshow has been rewritten to use closures, which protects its internal variables and functions from being overwritten by outside code. And the actual code to do this, on 447, they show you and on the screen here, they show you the library slideshow.js file. Again, it's similar to what we saw in the last chapter, but it's a little different as far as how things are arranged. First, instead of an object literal, this code starts with a function called createSlideshow, as you can see at the top. The function creates a timer variable, a Boolean play variable, a numeric speed variable, a nodes variable, which is an object literal, and an image variable, which is an object literal. So rather than having one big object literal, it creates a bunch of variables, two of which are object literals. The main JavaScript file is shown here and also on page 449 in the book. And in this version of the slideshow app, you have to create the slideshow object before you can use it. And the reason for that is because it's a closure returned by an outer function rather than a global object literal as it was in the earlier chapter. But again, the whole idea behind this is you want to protect the variables. And that's what you're doing by using a closure. All right. Let's leave closures for a minute and look at callbacks. When you pass a function as an argument to another function, the function that you pass is called a callback function. We've looked at this a little bit earlier with things like setTimeout, all right, and the sort method of an array. But now let's talk about it in a little more depth and breadth of coverage. So please remember that in JavaScript, functions are objects, which means that functions can be returned by other functions and functions can be passed as arguments to other functions. When you pass a function to another function, all right, the function that is passed is a callback function or a higher order function. When a function is passed, only its definition is passed. The function itself is called later by the function that receives it, which is similar to assigning a function to an event handler. Why would you want to do this? Two reasons to use callback functions. Number one is they create asynchronous code in which you pass the function at one time, but it won't be called until later. Second, it allows you to create utility code that is flexible enough so it can be used in a lot of situations with a lot of different data types. So for instance, with some of the stuff you see in here, you could include arrays of different types. Now, to make sure that this works as proficiently as possible, you want to make the callback function an optional parameter. You want to check to make sure that the callback function exists and is a function before you call it. And if the optional callback function isn't received, you want to do some kind of an action. So again, we saw set timeout earlier in here, and with set timeout, the function to be called when the specific interval elapses. That's your callback function. With set interval, it's the function to be called when the specified interval elapses. With add event listener, it's the function to be called when the event is triggered. With array.sort, it's the function to be called to sort the array items. And with array.reduce, it's the function to be called to reduce the array items to a single value. So what they show here on pages 452 and 453, and on the screen here right now, is they have a utility function that accepts a callback function. Remember, when you use callback functions, you can write utility functions that are general purpose, which is the idea here. So callbacks provide flexibility to handle complex or simple requirements within the same function, and that's the idea. All right. So here's one with no callback, and here's one with a callback. So the idea behind this, although sometimes when you look at it, it appears almost as though this is making your code harder to understand. The idea is, ideally at least, it sounds a little weird, the idea is ideally, but what's going to happen is it's going to simplify your code. You'll have less of it. If a callback function uses the this keyword, you can use the call, apply, or bind method to set its value, which can help you create and use callback functions with optional functionality like we just happened talking about. The function that receives and invokes the callback function can use the call or apply method to set the value of the callback's this keyword. The code that passes the callback function can use the bind method. Okay, doing this will prevent the this keyword from being set by the call or apply method in the receiving function. Again, read it, read it, read it, read it, read it. That's all I can tell you. All right. The last thing that's discussed in here about the last about the last 4 pages, and then there is an example afterwards. But the next 2 to 4 pages talk about recursion. Now, if you've never heard this before, they're talking about factorials right here. And that's always a popular way to talk about recursion or to introduce recursion. So I'm going to see if I can, well, that should have opened something and it didn't. There we go. All right. If I'm working with a number, I guess it opened it twice. And I want to work with a factorial, which is used in math and a bunch of other stuff. So if I want to say 4 factorial is equal to 4 times 3 times 2 times 1. But really, 4 factorial is actually equal to 4 times 3 factorial. And 3 factorial is equal to 3 times 2 factorial. And 2 factorial is equal to 2 times 1 factorial. And 1 factorial is equal to 1 times 0 factorial, which is 1. So the point is, what you can see is there's a pattern here. So although they've done the example that they're showing on the screen right here using a loop, okay, there is technically a faster way of doing it. Whether or not it actually is faster is a matter of opinion. But what they're doing here, if you look at the second example, is now from within calculate factorial, they're calling calculate factorial. So a recursive function is a function that calls itself. So recursion is a form of iteration where the function repeatedly calls itself. Each call should produce a smaller and smaller amount of data until you find a base case and you're done. Recursion is often used with hierarchical data like the DOM. It's best practice to use named function expressions within recursive functions. To name a function expression, you code the name after the word function and before the parameter list. Well, let me just tell you too, that there are many people who believe that you should never use a recursive function. I tend to not lecture on it much because what happens is every time a function calls itself, it has to take and make a copy of itself and all of its variables, kind of a snapshot in time, and put it out on the stack. And then the next time it calls itself again, it's got to do it again. All right. So what can happen is if you write a program with too many recursive calls, it can slow down processing to almost a crawl. So they're talking in here about how you can hopefully fix that. But again, my suggestion is use it as little as possible. Where you have a recursive solution, literally 100% of the time there's a non-recursive solution. So this example goes through a binary recursive search function. And just so you know, a couple things about a binary search. All right, let's assume here, I'm going to bring this back up. I'm making this up. These mean nothing. But I want to put 10 numbers on the screen here. In fact, let's leave it, we'll make it 7. All right, so we've got these numbers right here. All right, if I want to use what's called a binary search on these, then the first thing I must do is I must take these numbers and I must sort them in ascending order. So I'll have, what, negative 333 followed by 8, followed by 44, followed by, and I've got 55 in here twice for whatever reason, so let's make that 5566. So we'll make this 55, 234, 777, and finally 5566. So that's our original list, but they're now in ascending order. Okay? When I work with a binary search is what's known as a halving. And that's not misspelled. Halving sort. So the stuff must be in sorted order. Then let's say that I want to come in here and I want to know, is the number 1000 in my list? Again, you can look at this and tell. I understand that. But I say, okay, 1, 2, 3, 4, 5, 6, 7. So I cut it off right there. And I say, okay, is my number higher than that number? And the answer is yes. Okay? So I know already that none of those numbers can be the number. All right? So what I'm left with are these three numbers here, here, and here. So again, I cut it in half and I say, is this the number? No, it's not. Is it bigger than this number? Yes, it is. So now in 2 looks, I've removed 6 of those 7 numbers. And all that's left is to look at this. And is that 1,000? No, it's not. So I'm, okay. If you've ever played a little, I've done this with my kids, or I did this with my kids when they were young. Play a guessing game with your kids and say, I'm thinking of a number between, you can even say 1 and 1 million. All right, so let's just do that so you can see it. So I'm playing a guessing game with my daughter. All right, and let's say she's old enough. She thinks of the number 321,157. And you think, I'll never guess that. Well, the first thing I do is I guess right in the middle, 500,000. She said, no, it's lower than that. Well, now I know that I have now removed at least 500,000, actually 500,001 numbers. So I cut it in half again. And I said, okay, 250,000. She said, no, it's higher than that. So I know in 2 guesses that the number must be between 250,001 and 499,999. And I know that in just 2 guesses. So I've already removed about 2/3 of the numbers that are in there. So I cut it in half again. And I don't know exactly what that would be, but I'm just going to make something up. I'm going to say that I'm going to guess 350,000. She says, no, it's lower. Well, now that she says it's lower, I'm going to get rid of this stuff. All right, so now that I know it's lower than that, now I know that the number must be between what? It must be between 250,001 and 349,999. Remember, I've only made 1, 2, 3 guesses. So I'm going to cut it in half again. All right, and I'm going to say 300,000. And they say, no, it's bigger. Well, now I know that the number has to be between 300,001 and 349,999. So again, I go halfway and I say 325,000. And they say, no, it's lower. Well, now I know that the number must be between 300,001 and 324,999. And hopefully what you understand is what I've done is I've made 1, 2, 3, 4, 5 guesses. And I've already whittled down that I know what the number is. Pretty much I'm within 20,000 of the number, or pretty close to it, in about a half a dozen guesses. And I keep doing this, and eventually by cutting this in half and cutting this in half, so again, when I did it again, it would now be what, like about 313,000. Okay, and they're going to say, no, it's bigger than that. And then so that I know it's between 313,001 and 324. So I'll say 320,000 as an example. And they say, no, it's bigger than that. But you can see how I'm closing in on it rapidly. All right. You can also write this kind of thing recursively. And that's what the author has done right here, is they've made a recursive binary sort. So again, it's a halving sort. It starts halfway or the midpoint of the array, and it looks for a value to see if it's lower or higher than it. If it's lower or higher than the number you're looking for. So the example that they use in here, they get a random number between 1 and 1,000. They find in the worst case it's going to take them 9 guesses. All right, turning up to page 460, the chapter on 460, I guess through the end of the chapter, so the last 8 pages or so, presents the task manager application that we worked on in chapters 10 and 11. But now in this chapter, they've improved it by using closures and callbacks. So the app accepts task information from the user, stores it in local storage, and displays the tasks with a delete list. This version has been rewritten to use closures and callback functions. It also has bold exclamation points button right there, and if you click that, all right, the idea is if you click that, it'll make all bold tasks anything that has an exclamation point in it. You can see it right there. The closures that are in the example make the app more stable by protecting its internal operations from being overridden by outside code, and the callbacks make the storage functionality more flexible. So the storage library file, which is shown on page 463 and on the screen here, uses callback functions to create a storage library object that is more flexible. Here, applications can pass callback functions that determine how to transform the data the library gets and sets. And these get and set methods check to make sure that the callback functions both exist and are functions before they're actually called. The task list library file, which is shown on the screen here, uses closures and callback functions. Starts here with a create task list, which declares a variable named tasks that holds an array, a variable named storage that holds the object returned by the getStorage factory function, and a variable named sort that holds the function for sorting the tasks in the array. Finally, you've got the main JavaScript file. Again, the idea here is ideally at least, we'll have less code with each one of these iterations that we do. That although we're using more complex functionality, it should hopefully result in code that's easier to read, easier to understand, and probably most importantly, easier to maintain. So here's the main JavaScript file. It calls the create task list function to get the object to work with the tasks and passes it to the task divs and to the delete from task event handler function. The bold exclamation point function uses recursion and it walks the DOM. And what does that mean? It means that what's in the DOM, amongst other things, are what's in here. And it's looking through all of this, and if it sees anything with an exclamation point, it's going to bold it. So the idea behind this chapter is that you should hopefully understand what closures are and how they can make your code more stable, what callbacks are, how they can make your code more flexible, and what recursion is. Again, I'm not a big proponent of recursion. Okay, that's pretty much it for this chapter. When I come back in just a couple minutes, I'll be going into chapter 15. And chapter 15, which starts in your book on page 473, is entitled How to Work with Namespaces, Modules, and Custom Properties. I'll be back with that shortly.